All right. The thing went red. That means we're live, everybody. Hey guys, what's going on? Memes here. Yes. There's a dude, there's a whiteboard, and for some reason I seem to have some squirrely tail coming out of the side of my head. Must be a consequence of liking squirrels or something. But today we're going to be talking about building a balanced universe. And what do I mean by that? Well, flowing through all, there is balance. It's not just part of the Grey Jedi code. That is a claim. Whose claim? My claim. I'm sure plenty of other folks have claimed that at some point or another. But as we let folks come in from wherever on the internet they may happen to herald, whether it's a YouTube search, an algorithm that happened to bring you here that assumed you want to see some dude with a whiteboard talking about how we could build a balanced universe, so to speak, small u. Uh, Whether it's the X Twitters, the Blue Skies, some Discord server, somebody just sent you this because maybe they happen to like it and they happen to spread it around. I ain't the boss of you. Feel free to interact however you would like. Yes, cheesy self bitches this side. Oh, welcome, David. It's good to see you, my friend. Okay, we're gonna get into some stuff that it's gonna be a little bit of a review for folks that have been around for a little bit there, but I just want to lay out, and again, I am not a licensed quantum mechanic or anything like that. I'm just a dude, like a lot of y'all, that happens to find science interesting. I also spent far too much time yelling about politics, so that kind of burnt me out. But all I know is within science, we can better understand our realm of persistence, what's actually going on to higher levels of precision. My claim is if we science our way into this, we can science our way out. Uh, I'm, I'm just saying that if in a very short period of time, literally within, let's say, the next generation, oh, it's got quite a ring to it. If within the next generation, we could literally actually unlock scalable fusion and basically once you solve the energy crisis, you solve a whole crap ton of other problems within humanity and everything. If people still want to fight, they can just get in the ring and beat the snot out of each other. That's my take on it. Okay. So today, I'm gonna need a marker. My marker's over here. Okay. So what we'll do is we'll erase some of this. We'll let some folks join us on this fine Friday evening. Yes, we're talking about some science on a Friday night. And whether you're here for any of the science at all, or just happen to, for some reason, find it soothing in an ASMR style thing. I'm not gonna lie, I listen to a lot of science videos and just fall asleep because I'm like, there's a bunch of words. I don't always understand what's going on, and low volume. Certain voices have that effect. I think I first it kind of started to make sense when I think it was it Professor Brett Weinstein at one point said he had this lecture in college, and no matter what, by literally after the first hour of the lecture, he just always found himself dozing off. And he's like, the lecture would just go on in this tone, and I feel like it's one of those personal sleep tones, and especially if it's maybe a little bit more of a later in the day class or something like that, where maybe you're kind of burnt out. Maybe the caffeine is running on empty, and yeah, some noises will just push out. That's the more I think about that, it's I don't know. I feel like I can feel like my consciousness is waning at some points. Okay, so where are we gonna start? Well, let's start with actually no, let's use the pictures first. We don't need to scare everyone off too fast here. We'll employ pictures because we have them. And this was the poster that I presented. Well, technically presented at the hotel the night before, and I thought for maybe like 5 minutes actually at the conference. But let me share the class. Let's bring this guy up here. Okay, what are we doing? Oh my god! Oh, there, buddy. I must have clicked something wrong. It's no. No, I am not sharing all my system settings with you. Thank you very much. That was a little invasive. Where are we? Oh yeah, window. Here we go. All right, so this is ECC. is named after Sir Roger Penrose's conformal cyclic cosmology. It's basically the same thing, except a little bit of a twist. Rather than kind of the aeons, just we're going forward, we're going forward, we're going forward. I'm just saying we're recycling ourselves here. Okay, so let's get into this. What the heck is this? All right. So as we can see, this is not to scale number one. Okay, and after the discussion I had with Thad about what is the one, I'm like, well, if we're gonna claim this some and this is those cutouts. This right here is basically this is a steel version of the complement of the hyperbolic figure eight knots. So with knots, you start off, you have the unknot. It's basically just a circle. It's like just a string that's attached. It's the unknot. All right. Then you get the trefoil knot, or a lot of people's favorite knot where you just kind of cross over there. Okay. You go up one more knot. You add in the additional crossing along with kind of a Mobius twist there. You get the figure eight knot. And that's the first knot that projects a hyperbolic complement, aka a toroidal structure. And at least according to Kurt Mungel's interview earlier with the Professor Eva, God, forget your last name. I apologize, from University of Barcelona. But tori are important. You see a little figure eight knot there. These cutouts are for visualization purposes. Okay. So if we're going to claim that there's something like that in the center of our realm of persistence, or maybe if I say the word universe, I'm going to be using lowercase u, because capital U universe technically encompasses all things. I believe, well, a realm of persistence. Why? Because we're putting a finite limit of it, or at least we're going to claim the physical vastness of our universe is ginormous, about 100 million times larger than what we currently observe, but there is a limit. Basically, out here, there be dragons. I don't know. Okay. But the whole thing is, if this is here, and this is spinning around, and it's got a little throat there, it's about 10 to the minus 18 meters, approximately. Some people may say the conjectured radius of a neutron, or something like that. The Compton wavelength, no. Radius of either a proton or a neutron, or something like to some limit, which number one, I find is interesting. Okay. But if this has the ability to, let's say, suck things up, kind of like, I don't know about you, but back in the fifth grade, I learned about vortices. What do? We attach two-liter soda bottles together. You fill it with water. You have that little connection. You give it a little spin, and it goes around, 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 and then it comes out the other side. All right, that's essentially the claim about what's going on in the universe, so to speak. So what is that doing? Well, obviously, that's acting as an oscillatory network engine. Why? Because the acronym leads to one. And that's a reference of one for different stuff and things, is the claim. Okay. So, yeah. Basically, if you got this thing zooming around the center there, and you got stuff going in, now we'll get to the claim genesis of universe. Wow, talking about cosmogenesis. I am going to anger all the cosmologists. I apologize, Professor Keating. Let me commit my blasphemy for now. But if this thing is spinning around and it's sucking up stuff, whether it's black holes, superclusters, clusters, and it's getting compressed down to about 10 to the minus 18 meters. Very, very small thing. What might come out, I don't know. Is it going to seem like a quark gluon plasma? Maybe it's just a whole bunch of neutrons. Maybe it's neutron decay cosmology all the way out. All I know is if that starts expelling, because if you have an input, you've got to have an output. Okay. And if this input is about the magnitude of the Planck mass expressed in meters, really, really, really small. It's maybe like smaller than a grain of dust, but it's there. It's sucking up everything else that's out there and it's expelling it out. Now, what might that do? Now, if any of you all have boiled a pot of water, you're going to notice there's this thing that we generally call convection. What's that mean? You got your hot stuff. It tends to, it seems to tend to rise because it has more energy, but technically it's more like the cold air technically doesn't fall and stuff like that. I actually had some, actually, I think it was a retired programmer that told me that. Uh, Basically, your hot stuff, the molecules have more energy. They're bouncing around, they're more energy. They rise to the top. Okay. And then as things cool down, it's all right, you kind of go down there. All right. So all I'm saying is add in what we learned from the fifth grade, utilizing soda bottles and fluid, and apply a little heat to it. What's going to happen? I don't know. Maybe most of our observed effects? Just a hypothesis here, folks. What's that mean? Stuff goes in, it gets crunched down, it gets spewed in a much more hot state. As that's spewed throughout the cosmos, it goes around, and then all that matter starts to accrue into stars, galaxies, maybe a bunch of dust. And then as you're going through there, you're going to get your clusters. You get your super clusters. You get your black holes, your supermassive black holes, and the cycle repeats ad infinitum. Uh, that's the claim, and that's where we get eternal for, because it looks like if this claim holds up, and again, I'm sure there's plenty of ways we could disprove it, um, that would mean our realm is finite in size, but eternal in time, or at least from a point going forward. Is it always in the past? I don't know. I wasn't there, but we will get into conjecturing on what might actually be going on. And okay, so we got some mass here. Let's go to. Hold on. Why are you not? No, it hates me. Rebelling. Hold on. Ah, hey, Laszlo. Welcome, my friends. Balance equals chaos. I'm not sure about that, although, to be fair, here's the interesting thing. If we're going to go down the route of entropy, a lot of folks saying entropy is always increasing. I'm like, maybe? What if it's, because a lot of people, folks will say entropy. Oh, we just need thermal equilibrium, blah, blah, blah. Just okay. I mean, is that maximal entropy? I don't know. I seem to put out a lot of entropy. I'm just saying that human beings on all seem to have a lot of entropy, in my opinion, there. Could be wrong. Welcome, Hex. Thank you for joining. Turtles. Well, I mean, I am very biased to that, and where was it? God, I've been doing this for a while. I think I've been doing this so long that I may even have a clip for that. Oh, what is it? Oh, here we go.
It's turtles all the way down.
I almost forgot about those clips. It's all right. It's time to learn.
I should learn all these memes.
Oh God, that was like 5 years ago. It's been so long. It's been so long. Hey, I'm competitive. How does this compare to Sir Roger Penrose's model? Okay. So Sir Roger Penrose's model, let me see if I can grab this in the window. So conformal cyclic cosmology. I don't know if do they have the picture in the wiki? No, the wiki isn't that great. So the cyclic model. No, let me just do images. All right. There we go. All right. Well, this is probably the best we're going to get right here. So let me stop that. I bring this up. All right. All right. So conformal cyclic cosmology. All right. So the claim is each one of these sections here is basically what Professor Penrose would refer to as an aeon. Okay. And then he's basically saying, we have our model, we have our model. And then once everything gets so cold, so dark, it's like, well, if it's just photons and photons aren't, if they're not really experiencing time and everything, eventually you'll get to a point where things are either just going to rip apart. I believe he says all the supermassive, ultramassive black holes, hypermassive, whatever, eventually will meet together and you're going to have a big kablooey and it will start over. That's the best of my understanding for that. Okay. The claim that I'm making here is, and this is, uh, and again, I'm as I learn more, as we get more observations, happy to adjust things. This is just an idea. So the claim is we're going through our standard, whatever may have happened. But as we have our standard map where it starts to spread out and things start to get go out and spread, the claim is, well, what if just rather than continue to go out like that, it at some limit loops back around. So uh, you're going, and we're just cycling through. Now you might say, okay, well, it's how could we do something like that? We surely would have noticed. Okay, so how to explain this? Okay, well, number one, we're going to get to how we got these numbers in a second. All right, this is 6 times 10 to the 34 meters in radius. All right, that's the claim. We're going to have other evidence and stuff like that. Again, the current observable radius of the universe is about 10 to the 26 meters. All you got to know is basically there's 8 orders of magnitude. So the exponent is normally 26 for our observable. This is 34. So that's 100 million times larger. Okay. So the claim is we're going to need to have better methods to measure for curvature that we could measure on that magnitude. I don't know precisely what that magnitude is. We may only need 2 more orders of magnitude of telescope technology. I think I tried to do a calculation before, and it was a while ago, and I used a number that was actually still off. Well, that's the thing. It's a scientific process. It's you get new information. It's like, well, this seems to make a lot more sense. Sometimes you have to cast aside an idea. I got to cast aside this idea that's fine. Uh, what we're going to do is we're going to go through some calculations after, fairly simple things. You can literally just go into Wolfram Alpha and just type the words, not even have to do the numbers. Literally, the toughest thing you do is solve for X. You just put an X and then a unit, and then you like hit enter. It's like being a wizard. You type in the right magic words, boom. Okay. So how we got to this, that ginormous number, okay, we have the conjectured radius. It's technically 1 over the Planck length, or at least its magnitude is. Okay. Now, yes, when you get this out, how do we explain reciprocal meters? How does that make sense? Okay. So there's a couple of ways you can do this mathematically. But one of the reasons why I put this on the poster was reciprocal meters. Well, the inversion of a hypersphere is a torus. So if we started with, I don't know, a torus-like thing, and we inverted it, and we got a hypersphere. Thank you, John Williamson. May you be at peace. He was the first to point that out to us. Yeah, that seems to be its complement, or its at least inversion. The properties you get is total diameter. All right, so about 10 to the 35 meters. The content, this coincidentally, these numbers are actually the same. It's just the difference is the higher meter thing. And when you're calculating hypersphere, I think it's like another 2 pi squared factor. So it's like another 2 pi squared, and then you go up another dimension and you throw in another one of those guys. Uh, it's something like that, but okay. So what are we saying? Okay. Maybe we got something like this, something really small. Maybe it's rotating around. Maybe it's the Planck frequency. What's that? It's about 10 to the 43 hertz. That's a lot of hertz, my friends. What's that? That's frequency. So like a lot of TVs that it's you want to watch sports, you want at least like 120 hertz, about 100, 240 hertz. That's typically the refresh rate per second. I'm just saying if you had a TV at the Planck frequency refresh rate, gonna be smooth like reality. Why? Because that probably is what it is. Uh okay, so and ultimately here, this is the standard electromagnetic charge thingy with a source and sink. Ultimately, what we're saying is if there's something to this, and we'll get into stuff that does not require this in just a moment. So if you have this as a source, your galaxies and everything are flowing around, they're doing the thing, we're going on for billions and billions and billions of years. Eventually, you get to some point where it's going to kind of be some older stuff around. And at some point, we're probably going to flow and want to be, let's say, a multi-planetary species at that point. Because to be fair, I mean, where are we out here? I don't know. Probably about 14 something billion years away from here. And also, I'm going to make a very bold claim. Bold claim that small U universe is a little bit older than 14 billion years. Why? Locally, we may have come around about 14 billion years ago. As a whole for the system, I I'm thinking it's probably been around a lot longer. Why? Because at that point you have more than enough time for a lot of stars that were to collapse into black holes, and especially if more recent observations seem to hold up that where there may be direct collapses without like galaxy like brightening supernovas that like outshine the entire galaxy. If you just kind of have a collapse, a slight poof, like there'd be a bit of a flash, but like 3% of it is just kind of like a dust shell rather than just like a cosmic kablooey that's like it's probably going to be a lot more dark matter that we know, whether it's a black hole or a mass hole, whatever those might be, or neutrinos, whatever those might be. If you have a lot, if basically if we have more time for more just standard things that we know to have happened, might there already be a lot more dark matter out there? Again, that's even a separate thing right there. But Laniakea. Here's the thing. Oh yeah, no, I used the Laniakea picture right there. Yeah, that's like straight out of Wikipedia or something. Yeah, I just kind of cut it out to put it over there. Uh, well, the terrifying thing is here's the terrifying thing is Laniakea seems to be one of the most ginormous things that we can try to comprehend, and then even it seems to, or was it the Great Attractor is being attracted to Laniakea, and then there seems to be even more massive things. So if we're seeing and observing via James Webb and other telescopes, if we're observing cosmic structures that seem to be much, much, much larger than we had perhaps predicted, or according to a number of previous models, might it be because total system is much, much, much larger? I'm biased here. I think it's about 8 orders of magnitude. So, yeah, roughly about 100 million times larger than our current observable universe. That's very ginormous, but it's not infinity. Number one, see that's the part, and ultimately, at some technological level, we would be able to observe this, or at least test for it and see if memes. You're just full of it. Okay, hey, throw the idea out the window. I'm sure people have much better ideas. Okay, let's see what else we got. Could the inexorable emergence of super advanced host theory of everything consciousness being part of this model be the reason it's a strange loop to ensure it's a I mean that's going beyond the ontological bounds of this live stream right here. I mean that's a fantastical question. I don't know. Um, it from a philosophical perspective, it gets the old noggin jogging. I'll put it this way. Um, Hypothetically, if one was to create universe, whatever that might be, whether it was all I know is if I was a game dev, I would put a lot of Easter eggs in my game just so folks could come across them and be like, that's odd or that's interesting. All right, so the quick thing I have for the totally unrelated thing of this is where is it? I'll share with the class. Go window share. Well, from Alpha, I believe it's how do we do it? Oh, I think it's the is it, oh, a kilogram over kilogram squared over the boson. Believe that's it. I think that will give us, let's see. Try you again. Reload. Oh, wow. The LLMs are doing Z boson mass. Okay. So that gives us, okay. So when you take kilogram squared over the Z boson mass, you get that energy equivalence. You get about 6 times 10 to the 24 kilograms. What? Don't worry, that shouldn't mean a dang thing to you. What does that happen to be? Uh, kind of close to the mass of Earth. That's that's interesting. Our the Z, which I think is I don't think it has charge. I think the W plus and minus has charge. I think it's a neutral boson. So I just think that's kind of interesting that when you actually plot out it. I did a quick God no I did a speculative live stream about this I think like a month or two ago. Because this is just numerology as far as I'm concerned at this point. It's like again, numerology is numerology until it explains more with less. Um, my big thing is I'm happy with coincidences. And if you look at a lot of the particle masses, you'll see them at like really, really small things, like 10 to the minus, like usually like 24 to about 10 to the minus 31 kilograms. You start looking at like structures within the cosmos. It's very interesting. If you take the inverses of the particles and you just put kilograms squared over them, you get very. I'm just saying, if I were going to put Easter eggs in, I find these things interesting. Hey, Jax, good to see you, my friend. Good to see you. But yeah, okay, yeah, that's right. Z is neutral. Okay, that makes sense. Because I would just say my initial thought is, and again, I just look at it, I'm just like, oh, that's kind of an interesting thing. The mass happens to come out to be something similar. The Z boson is neutral, and well, Earth seems to be the reason why that we're here and everything. So, like, if it was highly charged one way or another, and does have its own charge and everything like that, but a lot of stuff cancels out, so we happen to be able to exist, which I think is a very personally to me, it seems like a miracle on its own. Uh, okay, so that's that tangent aside. Where were we at? Oh, let's go back to our little picture here, and then we'll do some very there's some simple call it math, call it analogies. It's like this is to this as this is to that. I don't know. It's like again, I stopped really understanding math halfway through the sixth grade, where our teacher's like, teach you this now. You don't need to know it now, but it'll be useful later. She taught us how to cross multiply fractions. So I was just doodling away in my notebook and everything. And then ultimately it's like, all right, go on to the seventh grade. Now that you know how to cross multiply fractions, here are some letters. It's lost all the way until like, I think nuclear chemistry and upper level finance class. And I took modern physics as an elective in college. not knowing I was supposed to take physics 1 through 3, all the labs, thermodynamics, and electromagnets. I was able to calculate the mass energy of a particle going x times blah 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 the speed of light. It's one of those things where if you have interest in something, at least for me personally, I'm much better at picking it up or at least being able to learn. Like video games kind of taught me a lot of calculus because it's like, all right, well, if I do this and I do this, if I change this, it's going to have a change in this. It's going to affect this. I need to factor in these things as well. And just, I don't know, I could just kind of feel it. That sounds very goofy. Spent a lot of time on ThoughtPod. Well, see, this is a very interesting thing. Uncompetitive brings up that the kilogram is an SI unit, which is tied to a volume of water. Okay. Now, one of the original formulations of SI, we literally just use water. Why? Because, well, the approximately, what is it, like 1 milliliter of water or something like that is approximately 1 gram. And then it's like when you get 1 liter of water, it, it fits very well. So and again, we officially kind of got away from that, but I believe there's a pressure and temperature that you could have where I think water lines up really dang well with the metric system there. So that is another story. Uh, right. Most recently, yeah, they're using it at sea. Because in this is actually something worthwhile because you basically hear nobody really talk about this. SI redefinition. Okay. So here's one of the things that happened, and this came to me because originally I'd gone out to the Physics Monastery and I'd come here and started to do these videos and let me take some of Thad's equations and reproduce them and show them to folks, and not even necessarily knowing really what's going on. And not to say that I know what's going on, but I feel like a little less in the dark now. Uh, but basically, while I was trying to redo these things, I was redoing one of Thad's calculations, and I look at them like, well, these numbers don't line up to the things on code out of here. What's going on? And then I noticed to the referenced data that Thad had, and it didn't match what was on code out. I'm like, what's going on? So what ended up happening is, let's go over here. So there's an SI redefinition that started in like 2019. Okay, so back in 2019, they had begun the rollout of the SI redefinition because let's go to Wikipedia article. Okay. I don't know. This Wikipedia article might be very biased, but actually there are some people that are really not happy about this. Hey, Keishal. Good to see you. It's the American letterhead paper. Oh. See, my thing is I'm like, okay, we've had modern printers for like, I don't know, 30, 40, 50 years. Yes. 50 years later, and we still get paper jams. Why is that? Actually, I think as Uncompetitive was talking about, probably because of water. Technically, I think I think I talked to a print tech before when they were fixing something. They're like, listen, you can only control like the moisture in the air so much. And if you're trying to crank out like hundreds or thousands of copies or something, it's going to get a little bit off and you're going to get a jam. So it's paper jams. I don't know. Is it like taxes unavoidable? I don't know. Does the IRS still exist? We'll see. But so basically what they did is, okay, let's just read from this real quick. From our friends at Wikipedia, in 2019, 4 of the 7 SI base units specifying the International System of Quantities were redefined in terms of natural physical constants rather than human artifacts. Did I spell artifact? Okay. Such as the standard kilogram. Effective the 20th of May, 2019. Wow, you can tell this was done by somebody that's not in the US because apparently we're the only country that you would put May 20th, 2019. Everyone else actually Starts with the date and then the month. The 144th anniversary of the meter convention. The kilogram, the ampere, Kelvin, and mole are now defined by setting exact numerical values when expressed in SI units. For the Planck constant, H, the elementary electric charge, E, the Boltzmann's constant, K sub B, and the Avogadro constant, N sub A, respectively. Second meter and candela have previously been redefined using physical constants. All right. So basically, they redefine stuff. So here's the old SI. Here's a diagram. Why? This. So you're like, oh, it doesn't seem to be all connected. We seem to be a little bit off. And then this thing makes it better. Except for maybe some chemists are not too happy with, I think, the redefinition of the AMU. Some people might be better, but no, you're at least looking at it, and it does. You're at least seeing the connections. Okay, C leads to the meter. Okay, so this is a hyperfine transition of cesium for the second. You got basically Planck's constant there for the kilogram. We got Avogadro's number of the mole is still kind of out here and everything, but listen, hey, we set it to a number and everything, and there are interesting things going on there. All right, so elementary charge for the ampere. Yeah, when we kind of go around. Okay, so amperes in charge, seconds lead to ampere. Okay. So that was a thing. So they redefined them. And after the redefinition, some of the numbers on code data had actually changed. Since the code data numbers had changed at first, I'm like, well, I'm going to have to ask that about this. So then we sat down there and we go on there and then we found out, oh, the numbers are changed. And we really weren't sure why until literally just I go to the website and it's like the SI redefinition. I'm like, oh, I did not know that this was a thing. So it's like, oh, simple question, simple answer. They redefine it in order to make it more accurate. So then we sat down, and that was the first time I got to sit down, crank out some constants and everything. And again, some of them have changed. And hey, maybe there was one or two that we had found that still stayed the same. I know they had just done the. It's really weird because they finally did the 2022 update back in last year in 2024. And you hear that and you're like, listen, you go through like some of the notes at some of the meetings there, and I'm like, this just sounds like standard parliamentary process. Because I mean, I was a senator from the student for student government and stuff like that before. I served my single term and then got out of there. But a lot of it is just like, all right, what's on the docket? What's on the agenda? Do we have any other measurements? How is the confidence? How is this done? How does it compare? If nothing's changed and you don't have any really convincing other experiments or any other reason to change it, you're probably going to leave stuff the same. So, I mean, it's people can disagree with it, but it's like, it's a process. Okay. So where are we at? All right. So we're over half done with the show, and I haven't even got to how we're going to balance it out. Let's go over here. Let's share these friends here. Okay. So we're going to do this a little bit the other day. This guy. All right. So let's our friend Wolfmouth. Okay. So we had a claim before over that radius there. It was like 6 times 10 to the 34 meters. How do we get that number? Okay. So here's how we magically get that number. Number one, personally, I like using brackets. Why? Better to not need it's better to have them and not need them than need them and not have them. Because I get very confused. All right. I'm gonna do meters squared over Planck length. Wait a second. Didn't I just do this for that fun-loving thing for the kilogram squared over the mass of the Z boson? You get approximately the mass of Earth. Yes, this is the exact same dang thing. Why? Squaring things is cool. Oh, look. This is that number that we had for radius of a conjectured radius of universe. Well, that just beat all. How big is it? So we do diameter, we will make that by 2. So um, basically, diameter is 2 of that. So if you half that, you would basically go up to about eighth magnitude. So about 100 million times larger. Okay. That's cool. Okay. So what does this have to do with something? Okay. So let's just say we were trying to figure out something else. So let's just put this on the board. Why? Because we're here. All right. So what do we do here? What we did is we just took a little bracket. We did meters. Oh, that was squared over Planck length, so L sub P. That's all. And the claim is that is radius of universe. Or no, let's write it out this way. I have an eraser. We can do these things. Radius uni. Radius uni. Okay. So we've got that. That's a big thing there. Cool. All right. So we've got a number. Why? Because we set units. Now listen, whatever you set your units to, you just want them to be coherent. That's the big thing. Because as long as your units are coherent, you could have it be like an Arglebarg or whatever. Name it whatever you want. But once you start looking at the relationships between different things, they're eventually going to hone in on something. And that's the whole point of SI there. And actually, the whole SI thing is, well, let's go to this. Coherent system of units. Let's do this guy. Okay. All right. Coherence. Yes. So we go down to a little table here. And this is one of the first times I had heard about this as well. Okay. So each variant of the metric system has a degree of coherence, the various derived units being directly related to the base units without the need of intermediate conversion factors. An additional criterion is, for example, in a coherent system, the units of force, energy, and power be chosen at the equations. I am not sharing this with you all. I'm sorry. There we go. God, dude is just making stuff up. Okay. It's this little chart right here. Okay, so force, we get our standard thing. Hi, Rick. Why I claim this is the radius of universe? Because Dad told me to. No, I'm just saying he had suggested it. It's where are we it's basically meter squared over Planck length. Gives you this number here. And also, if you happen to plug in that number into the hypersphere thing, you get those other things there. Is it right? I don't know. Is it elegant? I think so. And we're going to play around and we're going to present some additional evidence to try to support the case. And again, the case might be wrong. I guess we're going to have to follow the science, so to speak, and let experiments show. Oh, yeah. That little trolley thing there. Where are we at? Oh, coherence. So here's the thing. When you get force, so we got our standard F equals ma. Okay, what's that? Force equals mass times acceleration. Okay, well, mass is a unit, and acceleration is length over time squared. Because if it was just length over time, it would be speed, and then that would be momentum. So F equals ma, then we get energy equals force, so we've got our force, and then we multiply that by the distance. Okay. So you've got your force and how far that force can go. All right. Then we've got power. So the distance, you just be multiplying it by a length. So power is energy divided by time. How long can you maintain that energy divided by a length of time? And that's going to be your power. Why am I showing you all this first level physics stuff? Okay. So, in a coherent system of units of force, energy, and power be chosen so that the equations are the things that we just covered, hold without the introduction of constant factors. Once a set of coherent units have been defined, other relationships in physics that use those units will automatically be true. Einstein's mass energy equation, E equals mc squared, does not require extraneous constants when expressed in coherent units. So that's essentially the basis of one of the prime claims with what Fad has put out is if he happened to find closed forms for Planck units, and you can have accuracy up to as many digits as you would like. Ultimately, if you can get this to hold right here, you don't really need to have those other constants because you're literally building it from there. And if there has to be deviation, maybe around the seventh order of magnitude or going one way or the other, maybe there's a little geometry going on there, perhaps. But the whole thing is force. Okay, so mass. So if you have something for the Planck mass, an acceleration is length divided by time squared. You need the Planck length and Planck time. All right, check, check, check. Okay, and then that's force times distance. So that's a length then. Energy, you've got that. And how do you get energy? Well, what is that? I'm pretty sure electrical charge can help us with that, or a temperature. So then, if you had the two other forms of things that can do the energy type of stuff, uh, does that mean when our 5 dimensions combine, we get Captain Planet, Captain Universe? I don't know. Hey, Poindexter, good to see you there. Rick. Here's the thing. When I start off this thing, I hate the word universe. I always use, yes, I use it like that, lowercase u universe. I prefer realm of persistence. The words matter. Words matter because if you're going to say universe, big U universe, you're talking about everything, the whole shebang. If we're going to claim limit, or at least I'm willing to conjecture, there's a limit. Of course, you naturally have the idea, well, what's outside the RB Dragons? And people say, no, that's an ill-posed question. Really? That isn't the first thing that most everybody thinks of. It's like, well, what's outside? The Thadiverse. Yes, conjecture. Yes, welcome to my cosmological blasphemy of the week here. Somebody has to do it. Okay. So, yes. Hey, as long as we can get a few laughs, that's what matters. Oh God, people are laughing as we have just some Maxwell stuff up here. God, that's got to be just. All right, let's get back to where were we at here? Okay, so we did this thing. All right, now we're gonna do a different thing. We're gonna do this, and we're gonna make another claim. Let me get some water. So we're gonna take our same thing here, and now put the square on the outside. Why? We'll get to that in just a second, because that's going to give us a number. But since it's a meter divided by something expressed in meters, it's going to be dimensionless. So I get this big, beautiful number right here. Okay. So let's. Okay. When I first come across that, I kind of recognize that because that's like, if we're going to claim there's an inversion and there's a minimum length, well, then its inverted form should be the maximum length, or at least expressed in radii, so to speak. So that's basically where I got that. Originally, I think he had listed as a temperature because it was the outside domain. That was 10 to the 32, but 10 to the 35 is three more orders of magnitude, and it does seem to line up with some of the other stuff there. There's plenty of other stuff where it's like, oh yeah, if you just do that four-dimensional hypersphere with that ginormous radius in there, um, gives you it gives you this crazy number, this 3 times 10 to the 69 number there. So yeah, so that's why. Then all of a sudden I'm like, oh wait, it's just meter over Planck length squared. Duh. I mean, that's all it was. Okay. Now, if we were to set it equal to something, let's say well, we've got the Planck length down there, so let's do another Planck thing. Let's try the Planck mass. Okay. And then let's just solve for x kilograms. Why? Because this is a fantastical thing. All right. And we're not squaring that. Why? Well, E equals mc squared. So maybe we don't need the c squared. Maybe that's already on that side. I don't know. It's because of the number that happens to come out. You look at this, I'm like, all right, so that's the inversion of the Planck mass right there. And now it's doing for that many things. You get this ginormous number here. This ginormous number. 83 novum decillion. Or 8 times 10 to the 61. Let's do that one. Let's take off a butt ton of digits because it's making my head hurt. There we go. All right, let's go down to like 5. All right, so 8.33 times 10 to the 61. We're solving for x, and we're solving for kilograms. Okay. So we get that. Oh, look. About 100 million times more mass than the mass of observable universe. As we go through these things, we're going to notice there's about a magnitude of 100 million greater than the observable universe. That seems to be a corresponding thing. Again, this is just a really large number hypothesis right now. It's that means a lot, Poindexter. It's I mean, a lot of it's just I'm interested in this stuff. I happen to have certain means. I only have so many means. I don't have that fancy like $30,000 console universe simulating stuff. Just a dreamer with a mathematical notebook. And a lot of times I just go to Wolfram Alpha because a lot of times it's faster. Okay. So we get this, and let's proceed. Okay. So that's gonna be, let's go back to our little thingy over there. Now let's remove that. Okay. So we had that. Then let's do this. We'll do this again. We're just gonna do meters. Do over again. Also p the Planck length, except we're squaring it. And we're setting it equal to well actually that's the claimed. I'm gonna use the term mass bank because we can do the whole E equals mc squared. You can convert back and forth. I like the term mass bank of universe, but I'm going to be lazy and say that that's mass uni. Yes, yes. As Rick had keenly pointed out, that's we should be sus. We should be sus anytime we say the word universe. That's why you're doing small u uni. Okay, mass universe over uh, m sub p Planck mass. Okay. Now I wrote those words on the board. I did a little calculation. Why the heck should you believe? Number one, you shouldn't. You should question it. Because, or if you want, you can feel free to trust, but just verify. Does this make sense? Because if, okay, this is about 100 million times larger than the radius of the observable universe, and this is about 100 million times the mass of the observable universe. It's like, okay, coinky dink, show mo minky dink. How many coinky dinks does it take to get to what might be going on? I don't have a direct answer for you, and we only got like 5 minutes left. But it's something to chew on. It's something to just have some thoughts about. They also said, oh, just commenting, given the minimum step and a maximum distance, it's possible to calculate the data element storage size needed for discrete calculations. Dataverse may be discrete and computable. I mean, that sounds like it makes sense. I don't know. Oh, damn, there's so much to do. Oh, dark energy and dark matter. Okay, let's wrap up with this. When I say this is the mass bank, uh, I'll need more time to prepare just to kind of do it. But when you do this calculation, uh, what is it? The approximate ratio from observable matter to dark matter, it's about 70% more dark matter. It's like 30% normal matter, it's like 70% dark matter from the observed mass effect that we see. How does it go? Basically, this mass uni, that's why also using the term mass bank of universe, it does seem to include the dark matter, so to speak. Uh, or actually, no. We're going to claim or that is also does include the dark matter. Now, what is the dark matter? Uh, the dark energy does seem to be actually what's going on. So let's go back to our little thing. One thing I really wanted to get to, I didn't get to, but that's good. That's good. No, we're parsing through things and I'm learning. So that's the whole goal. So window ECC. Okay. So ultimately, the dark. Okay. So the dark matter, whatever that might be, I'm personally thinking, just in my opinion, I think it's mostly just black holes and neutrinos. I think it's a lot of the matter that we already know about. I think there's also a lot of cool dark matter because if age of universe for our system or realm of persistence is greater than 14 billion years, we may be kind of new kids on the block. If there's been a lot of stuff out there being able to go through stellar evolutions for billions and billions and billions more years, and you've had stars out there that have been radiating out neutrinos, uh, and if there is more or less direct collapse, stars, two black holes without galaxy shining explosions, it's probably just a lot more of the dark matter that we're aware of out there. And if that's the case, well, I guess we don't need to find axions and stuff. Listen, I'm not saying that there aren't axions or WIMPs or something like that. Well, to be fair, neutrinos are WIMPs. No, I'm not hating on the neutrinos. They're just weakly interacting massive particles. That's the acronym they use. The dark energy just literally, to me, and again, maybe it's just because I'm a simple person, it just looks like it's the flow. Maybe call it dark flow. It's looking like you might have, I don't know. There we go. You got a source, and you got stuff coming out. Eventually, if it's gonna go all the way around, maybe it's like, I don't know, about 10 to the 35 years or something like that. Not that okay, maybe I checked the calculation once. Uh, but if it's gonna take a ridiculous amount of time, at some point it's gonna come through here, and then it just loops around. And if at that point it's like, okay, it does that mean at some point or another you're going to get to the exact same configuration as we are, except instead of ordering pepperoni pizza, ordering a Hawaiian pizza? Maybe. Because if there's one thing I've learned from Professor Sean Carroll, it's that when dealing with infinity, that's a long time. I don't know. Do we get some form? Does that count as many worlds? If you have infinity and you have enough configurations, eventually we'll get to. I don't know. Does it solve paradoxes or does it create more conundrums? And then the more and more I think about it, the more disturbed I get because I'm like, what if we really aren't the new kids on the block? What if we really are the new kids on the block? Who are the old kids on the block? Then I need to start citing Babylon 5 and the old ones. Uh, but yeah. So I mean, again, it's the whole redshift, and maybe things are expanding. But I'm just like, if can we just explain this with thermodynamics? Stuff goes this way. If there's some rotation gradient to it, it's just going to go around, loop around, bomb, bomb. It's ultimately it's I remember when Stephen Wolfram at one point said it's like he's like, oh, he gets the call from Robert Ford. It's a theoretical physicist and science fiction author. Got a call in like early '80s or something. It's calling about the paper he did in 1981 with Jan Manjorn, and it's about the thermodynamic properties of the vacuum. And Robert's talking to him. He's like, "Are you sure your calculations are correct?" And Stephen's like, "Yeah, I'm pretty sure my calculations are correct." He's like, your calculations are correct, then there must exist somewhere something basically effectively mining energy out of the vacuum, basically a perpetual motion machine, or, for lack of a better term. And Stephen Wolfram says this on a live stream. He's like, and I look into what he said, and he's right. And I'm like, wait, 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 time out, time out, time out. Did Stephen Wolfram just casually say that there must exist somewhere a, a perpetual motion style configuration? What? What? I think I may have cited it on the poster. Because ultimately, when he delved into it, he's like, I don't think you could do it with actual matter because actual matter, it's you would need to have perfect opacity, basically meaning you would need to shield it from all electromagnetic waves, and you can't really do that by making something made of matter. But he conjectured, he's like, I suspect you could do that with some form of a field configuration. And I'm like, cool. I mean, ultimately, that's what we're proposing. But no one would order pineapple on pizza. See, that's actually no, that's a baiting question because I had to say Hawaiian pizza. You just do the pineapple on pizza things because it gets people all ornery because they're like, oh, why would you do that? But you're not a real kosher eater or you need halal or a halal eater or something. Uh, the saltiness of the pork does contrast with the sweetness of the pineapple, and you don't want it to be soggy because otherwise, meh. Who likes soggy pizza? Unless maybe you're from Chicago. But all right, before I start a pizza war, or at least another one, that's all we really got for right now. So yeah, we'll build some more building blocks next time. Maybe we'll get more than two thingies on the board. But other than that, peace out, everybody. Take care of yourselves. It's a wacky and wild world out there, and beware of people that order double pineapple on their pizza. I'm just kidding, Rick. See ya.